we are going to explore how we can calculate volumes of irregular shaped solids. So we're going to start with this basic solid, which is a right cylinder. The right cylinder basically means that we have two identical bases that they're on parallel planes, and one is directly above the other, and then their edges are joined along the border. Okay, so that's what a cylinder is. A lot of times you might think of a circular cylinder like this, or a lot of people don't think of this as a cylinder, but technically a box is a cylinder, like a rectangular box is a cylinder with a rectangular base. So those are all types of cylinders. And the important thing to note here is that if you have a base area A, you can find the base area A. And if we know the height of the cylinder, so that's the distance between the two parallel bases, then the volume of the cylinder is the base area times the height. So we're going to take that and use it to calculate the volume of some irregular shaped solids. So I'm going to just kind of draw some irregular shaped solid. So imagine this as some sort of a blob shape. And what I'm going to do is I'm going to set up some coordinate system, and all I really need is one axis. I'm going to call it the x-axis. And I'm going to say, suppose this blob all exists between the x values of a and b. And we are going to divide that interval into n subintervals. So we're going to divide the interval from a to b into n equal subintervals. I'm going to draw some representative interval in the middle. Each of these of width, which we're going to call delta x, which is going to be the length of the whole interval divided by n. So b minus a divided by n. And in each subinterval, so we can name these points. A is going to be x0, and then the next point is going to be x sub 1, then there's going to be x sub 2, x sub 3, x sub 4, and so on, all the way up to b is going to be x sub n. The previous one is x sub n minus 1. One before that is x sub n minus 2, and so on. So the first interval goes from x sub 0 to x sub 1. The second subinterval goes from x sub 1 to x sub 2. The ith subinterval goes from x sub I minus 1 to x sub I. In the ith subinterval, we're going to choose a representative x value, which we're going to call x sub I star. Sometimes that's chosen as the left endpoint of the subinterval, sometimes it's chosen as the right endpoint, sometimes it's chosen as the midpoint, and sometimes it's just allowed to be a random point. So I'm going to pick some x sub I star in that subinterval, and we're going to let a of x sub I star be the cross-sectional area of the solid at that x value. So I'm thinking about this, and I'm at this x value. I'm going to basically slice this blob, and I get some region that has an area. Okay. And note that at every x value, there's going to be a different shaped cross-section. Different shape, different area. So this area is a function of the x value. And then we're going to estimate the volume of a slab. So basically that subinterval from xi minus 1 to xi creates a slab of width delta x. So I'm going to see if I can draw this. So it's something like this, and we have an actual slab of width delta x. So the volume over the ith subinterval is approximately a of x sub I star times delta x. This is where we're using that volume of a cylinder. This thing here is a cylinder. It's in a different orientation. The bases are facing right and facing left rather than facing up and facing down. But this is a cylinder. Okay, so we estimate the volume of the slab over the ith subinterval as Vi is approximately equal to A of xi star times delta x. Then the total volume of the solid is approximated by V is approximately the sum I equals 1 to n of A of xi star times delta x. Okay. Now this is an approximation because the actual slabs cut by those subintervals are not perfect cylinders, because it's going to smoothly change from like the face of the right facing side to the face of the left facing side rather than be a direct cylinder. But we could get a good estimate with a high number of subintervals. We get a better estimate with a larger n value. And so our volume is in fact equal to the limit as n goes to infinity of this process, adding up these A of xi stars times delta x from I equals 1 to n. Hopefully, you've had enough experience with this now where you can recognize this as a Riemann sum. And so something that looks like this is in fact equal to the integral from a to b of A of x dx. Okay, so this is how we're going to calculate the volume of the solid by slices. And whenever we do this, it's important that we understand what our bounds of integration are. We're going to have to figure out what A and B are, and then we're also going to have to look at what that cross-sectional area looks like. So let's start with an example here. We're going to find the volume of a pyramid with a square base of side length 10 inches and a height of 5 inches. Okay, so that means this length here is going to be 10 inches, and also this length here is going to be 10 inches. And if I was to look at the height, that would be an internal amount here. That would be the height, which is perpendicular to the base, so that is 5 inches. So what I'm going to do here is I'm actually going to, you can think of setting up your x-axis to be going in this direction. I'm going to kind of make this dashed to indicate that that's going through the middle. So just so we have actually an orientation that we're a little bit more familiar with, I have plotted this same solid here with the x-axis pointed to the right, as we're a little bit more accustomed. So the x values are going to go from 0 to 5. Okay, that's because that's the height of the pyramid. And at each x value, I'm going to have some square, which is my cross-sectional area. Okay, so the area as a function of x is going to be some length squared. And I want you to notice that length is going to be changing as we change our x values. So the length is going to be a function of x as well. Now, sometimes it helps to kind of look at this in a slightly different perspective. So I'm going to look at this without the 3D rendering and just look at what it looks like on the 2D plane with x and y. Okay, and so I should have some sort of triangle like this that's going to be at x equals 5. And at the end where x equals 5, that distance is going to be 10 inches. So that means that this also has to be a length of 5, and that's got to be a length of 5, which says that this is the line y equals x. Okay, now for some representative x value, I have my length is here, and we can see the length is twice the y value. Right, so here's, let me put this in a different color. Here's the y value there, and then the y value associated with that x value, and then the length is twice the y value. So the length is twice the y value, and we need everything written in terms of x, so we also have the y value is equal to the x value. So the length is equal to twice the x value. That says, we take all this information and put it up here, and we have that the area, which is L squared, is equal to 2x all squared. Okay, so the area as a function of x is equal to 4 times x squared. That would make the volume equal to the integral of 4x squared dx. And we need to think about our bounds of integration. What x values are we integrating over? We are integrating x should go from 0 to 5. In each of these problems of finding volumes, the biggest challenge is going to just be setting up the integral, and then after that, you can evaluate the integral in whatever way you feel comfortable. So I'm going to complete this. This is 4/3 x cubed, evaluated from 0 to 5, which is going to be 500 over 3. And so the volume is going to be 500 thirds. What are the units here? Volume. So area would be in square inches, and then the dx is in inches. This is all going to be in cubic inches. So cubic inches. All right, let's move on. Let's find the volume of a sphere of radius r. You may or may not have some memory of the volume formula of a sphere. Okay, and we are going to calculate that using this method, using the method of slices. So I'm going to start by putting axes down. I'm drawing these in perspective, which means they're not going to look perpendicular. And I'm going to make some of these disappear. So this is a little bit of a perspective to show that sphere existing centered around the y-axis, the x and y-axis. And I'm going to think about this where I'm going to integrate with respect to x, and basically at each x coordinate, I should have a circular cross-section. Okay, so that should be my cross-section here. Now, there's this question of what is, so you know the area of a circle is pi r squared, but what is the radius here? Okay, so we're going to need to work that out. So I'm going to take a look at this again. I'm going to look at it on the flat xy plane. And I should have said, so at this particular x value, the radius is going to be the y coordinate. Okay, so I'm looking at some particular x coordinate, my radius is the y coordinate. Okay? So in this blue circle is meant to be the outline of the whole sphere on the plane. So we need to know what the equation is of this circle. It is, so this is a radius r circle. And basically using the Pythagorean theorem, we have x squared plus y squared equals r squared. That's the equation of the circle. So I'm going to say up here, the area is going to be pi times the radius squared, which is y squared. That is in terms of y. We're integrating with respect to x, which means we need to have the area written as a function of x. So rather than solving this equation for y completely, since I have a y squared, I could just solve this for y squared. So this x squared plus y squared equals r squared says that y squared then is equal to r squared minus x squared. So bring that up here, or bring this down here, and we have that the area as a function of x is going to be pi times y squared, which is r squared minus x squared. Okay, now to set up my integral, I'm going to integrate a of x dx. And what are my bounds of integration? Well, what x values am I integrating over? I should be going from minus r to r. So that's minus r to r. So the volume is equal to that, which is equal to the integral from minus r to r of pi times r squared minus x squared dx. Now, I want you to notice two things. One, this is an even function in x. Anytime you're integrating an even function over a symmetric interval, an interval that's symmetric across the x equals 0 line, that means I can rewrite this as twice the integral from 0 to r of that same thing. So this is a property of even functions integrated over symmetric intervals. But also look at the sphere. You know, this is the volume of the whole sphere is basically twice the volume of just the right hemisphere. Okay, that's integrating from 0 to r is just the right hemisphere. Okay, so this is now 2 pi times r squared is just a constant, so integrating that with respect to x is going to be r squared x, and then the antiderivative of x squared is 1/3 x cubed. This is evaluated from 0 to r, so this is 2 pi times, put in r, and we have r cubed minus 1/3 r cubed minus r squared times 0 minus 1/3 times 0 cubed. Okay, so putting that in as x equals 0 is 0. So this is going to be 2 pi times, we have r cubed minus 1/3 of r cubed is going to be 2/3 of r cubed. So our volume of a sphere ends up being 4/3 pi r cubed. Let's take a look at this one. So we have a wedge cut out of a cylindrical tree, and one cut is parallel to the ground, and the second cut is at an angle theta from the ground. And so we're supposed to determine the volume of the wedge. So this blue plane here is meant to represent the cut that is parallel to the ground, and then the purple plane is an angle theta from the ground. And so what we're looking at is this little tiny wedge in here, and I'm going to reveal that's what that wedge looks like. So what we're going to do here is I'm going to set up my axes. One of my axes is going to be here, and then the other one is going to be there. So I'm going to call this my x-axis and my y-axis. I want you to think about this as being like laying down flat and we're kind of looking at it from the side. And what we have here is, so I'm actually going to integrate this with respect to y, which means I'm going to take slices at individual y values. Okay, so if I pick a y value, say here, then I want you to think about what the slice is going to look like if I cut this with a plane through that y value. Okay, it should be something like this. It should go over to here and then up to that side. And it should actually give me a triangle. So I want to think about the lengths of the different sides of this triangle in terms of x and y. Okay, and I don't really have equations for the stuff that's outside of the xy plane, so I really want to focus a little bit on what's happening inside the xy plane first. So I want, for one thing, to look at this curve, which is in the xy plane. That's where this blue plane intersects that, the tree. So that is a circle, a part of a circle. And that should be, let's see. It doesn't say anything about the tree, so I'm going to assume that that circle has radius r. So semicircle with radius r. And so again, that equation is x squared plus y squared equals r squared. And when I draw this triangle, then this length down here is going to be whatever my x value is on that circle. And the other piece we have, like, so this vertical piece is not the y value. Don't go thinking it's the y value. The y value is here. Like, here's the y-axis, so the y value is relative to that y-axis. This vertical line here is actually sticking up out of the xy plane. So that might be a z value. We need to figure out what that means. And the information that we have here is that the second cut is at an angle theta from the ground. So if I look at this triangle, I'm going to recreate that triangle here. It's a right triangle, and I have an x here, and this is theta. So this here is going to be, this length is going to be x times tangent of theta, because that length divided by x is the tangent of theta, so that must be x times tangent of theta. Okay? And so then looking at the area of this cross-sectional slice, the area is going to be 1/2 base times height. So it's 1/2 x times x tan theta, which is x squared over 2 tan theta. Now, what are we going to do with calculating the volume? The volume, go back up here. Well, maybe I'll go here. The volume, we are taking slices at individual y values, so we're going to be integrating with respect to y. Okay, so we need a area in terms of y. We have an area written in terms of x, and this is our equation relating x and y. Okay, so again, this says that x squared should be equal to r squared minus y squared. Okay, so my area is x squared over 2 tan theta, and my x squared is equal to r squared minus y squared. So I can rewrite this as an integral of, I'm going to pull out the 1/2, so that's 1/2. And x squared is r squared minus y squared times tangent of theta. And that is dy. And again, my y values are going to go between negative r and r. Tangent of theta here is constant. This is not changing with y. The theta is fixed at the beginning of this problem. So it's a constant here. So I can pull this 1/2 tan theta out of the integral. And I want to point out again, this is an even function in y, and so I can multiply it by 2 and just integrate from 0 to r squared minus y squared. And you can see that in the picture as well. This whole volume is basically twice the volume of just integrating from 0 to r. Okay, so this is tan theta times r squared y minus 1/3 y cubed, evaluated from 0 to r. This is tan theta times 2/3 r cubed.